Okay, in this video, what we're going to do is take everything that we've looked at so far in regards to mathematics, and we're going to put it into good use. It's time to take a close look at transformations, which is very, very important.
This is why we did matrices.
Yes, it is, and it's going to make so much sense, hopefully, in just a minute. But in talking about transformations, what I'd like to do is spend just a minute, Joel, and talk a little bit more about matrices in relationship to OpenGL. OpenGL has several different matrices
that you can modify.
That we can modify, that each have a very specific purpose.
And they're basically modified over the course of your application.
That's right. If you guys think all the way back to the introduction VTM that we had, or video that we had in this VTM, we had the matrix mode set to the model view matrix.
Right, and then we reset it.
And
we basically explained it as we want to put everything back to its original location.
That's right, but what we were resetting was the model view matrix.
Right, and that's the matrix that basically sets where the objects inside of our scene are going to be placed.
That's right. Then we have other matrices.
Like our projection matrix.
For projections, for textures, etc.
Right, and we'll talk about that in the next lesson a little bit more.
Absolutely. So that's the very, very first thing that you guys need to understand at this point now, is that inside of OpenGL, we have several different matrices. We always have these matrices. And these matrices deal with the model view, which basically is where objects are created, textures, projections, etc. The model view is what we're focusing on now. So first, let's go ahead and jump over to our whiteboard real quick.
All right.
And we've got a very simple scene set up. Now, when we start using things like GL Translate and we're introducing new coordinates, we are directly modifying the model view matrix.
Right, and we'll see in a second we have our GL Scale, GL Rotate, and GL Translate that allow us to modify our model view matrix.
Right, in the model view matrix, just this one 4x4 matrix, but we can apply a GL Translate, a GL Scale, etc., and that one matrix is being updated with
constantly, right? There's only one matrix, one model view matrix that we're constantly modifying, and the OpenGL state is updating that.
So depending on how you do your rotate, a scale, and a translate, perhaps all at the same time, your matrix can start to look pretty complex.
Right, it starts stacking on all the transformations that you do.
That's right. Now let's go ahead and look at a very simple example of how the model view is working in regards to the creation of objects in our world.
Right.
So we're going to start out with a GL clear. So we've just cleared everything.
Right, everything's back to its original state.
Now, when you first initialize OpenGL, the model view is reset.
Right, it's set to its default identity state.
That's right. So we are at 0, 0, 0 as far as translate X, Y, and Z is concerned.
Right, basically we're located at the origin right there.
That's right. So here's what's going to happen in our very cheap example, okay? Very first thing after clearing is we're going to draw a sphere. So it's going to draw the sphere wherever the model view has us at the moment for creating objects.
And of course, at the very beginning, we're going to be at 0, 0, 0.
That's right. So we're going to make a sphere right there at the origin. That's a huge sphere.
Thank you.
Goodness. All right, the next thing.
Great sphere, isn't it?
That's right. We are going to use a GL Translate. So basically, we are going to directly modify the model view matrix such that X is now 5, Y is 0, and Z is 0.
Right, so basically our transformation matrix, our model view matrix, moves any objects that are drawn to 5, 0, 0.
Right, but don't let what Joel said confuse you. That can be confusing in a sense. It is going to move to that, but you'll see how this works in a second. Go ahead and make a tick mark at what we will say is 5, 0, 0.
Let's say that right there is 5.
It's kind of like this is where our focus is at the moment. So the next thing created is going to be created here. And the next thing that we create is a square. So we're going to draw a square. And that square gets created right there. I'm not laughing, honest. All right, very good. Now we have another GL Translate, this time 050, and here you're about to witness a very important thing. It's all relative. So this is not absolute based on the origin of the world. What we're going to do is, again, we're updating our model view matrix, our transformation matrix, in such a way that our tick mark is now going to appear 5 units directly above where we were at last.
So right
about there. Because you'll notice with that particular GL Translate, we did not modify X and we did not modify the Z component, only Y. All right, excellent. So now when we draw the cylinder, we're going to draw it right where our model view matrix has us. Right here. I actually said the matrix has us. Rock on. Okay, now we do our GL flush. So this is drawn out. The user sees it.
Right.
Excellent. Now, Joel, if you don't mind, from the GL flush all the way up to the GL clear, just draw the little arrow, just reminding everyone that we're in this loop. So now we clear everything out, and there's no reason to erase it. I want you guys to visualize what's happening. Now we're going to draw the sphere again, but at this point we have not reset our matrix. And if you go back and watch the introduction of this VTM, at this very point when we talk about resetting, you're going to go, oh, that makes so much sense. Draw the sphere where it's going to draw.
All right.
Check this out. It's right where the cylinder's at because that is where our model view has us.
That's right.
Excellent. Now we're going to do a GL translate. So we are, again, manipulating our model view matrix. So we're going 5 units positive in X, and we're leaving Y and Z at 0. Excellent. So now we're going to draw a square. Look where the square gets drawn. Now we're going to do another GL translate. We're modifying the model view yet again, going up 5 units in Y, X and Z are being left at 0, and we're drawing a cylinder. Again, we do a flush. The viewer, this is what's interesting. We do the flush. Remember, we did a clear a second ago.
Right.
So now the old cylinder and the old cube and the old sphere, the old cube, and the old cylinder, they've been erased because of that clear. Now
all the
what
user
they see
can now see is this sphere, this square, and this cylinder.
So it's like everything just moved diagonally up.
Yep.
Okay? Now, so that just, and this happens so fast that
you can't even see what's going on.
Yeah, exactly. But the concept of what's going on here is so important. Okay, so I'm just going to do this one last time. So now a sphere is going to get drawn.
So right here.
So right here, that's where our model view matrix has us. All right, then again, we go 5 units over, positive in X. So a little tick mark, that's where our focus is at the moment, if you want to look at it that way. We now draw a square. We now move 5 units up in Y. Now we draw a cylinder. And we draw this out. So again, everything has, again, moved diagonally up.
Right.
So everything's just the 3 items that we are drawing just
keep on shifting up.
Just keep on shifting diagonally up.
And of course, what we really wanted this code to do was have it draw everything, sphere here, square here, and cylinder here, and every time it refreshes, it should be in the same place. We're not looking for animation at this point.
That's right.
And we're getting it, so that's a bad thing.
And here's the interesting thing. We're getting it so fast, you wouldn't even see this.
Right.
So you'd be like, hey, what's going on with my application?
Right. So, and it's just going crazy.
So in this particular case, to make everything work right after the clear, we could go ahead and reset our model view matrix.
Right. This is where I think what we had was our GL.
It's a GL matrix mode, and we set the model view.
So let me just write this in real quick. GL matrix mode. Sorry. A little ugly there.
That's okay.
And then we did our GL
load identity. And we're going to talk about the identity matrix in just a minute, and it's going to be very clear how it works.
Right. So we stick these 2 commands right inside of here, and then everything will always be where they're supposed to be.
And in fact, let me talk about those 2 commands for just a second longer. The GL matrix mode, again, OpenGL has several different matrices, all with very specific operations in mind.
Right.
Very direct things they're working with. In our case, we're dealing with the model view, so where objects are located in our virtual world.
Right.
So we're saying, this is the matrix we're about to modify. So we set the matrix mode to the model view, and then we load the identity.
Remember that we're using OpenGL as a state machine.
That's
so
right.
Every time it has to know which matrix we want to modify.
That's right.
And all subsequent commands dealing with matrices will be modifying the matrix that you just set.
Precisely. So we set the model view, and then we come in here and we load the identity, which is basically just loading a reset matrix, a clean, fresh
clean
matrix.
slate.
That's it. And then at that point, we would draw our sphere in the right location. We'd then move over. We'd get our square in the right location. We'd move up. We'd get our cylinder in the right location.
And
it would get drawn out to the screen. It would go back around, clear the screen, reset that model view matrix, and draw everything again. At that point, running your application, you end up with your sphere, your square, and your cylinder staying put the way they should be.
That's right.
There you go.
There you go.
Hopefully at this point, we now have a sense of the model view matrix.
Right.
Joel, let's go ahead and jump back over to PowerPoint now. All right, so let's go ahead and step forward. Matrices. We've got several different functions here.
That's right.
that are very handy. The most important one is going to be the GL matrix mode, because this is how we're going to set which matrix we're currently applying our modifications to inside of OpenGL.
So the first thing, once we've set which matrix we're going to modify, we have basically four main commands that can modify the current matrix.
Okay.
So the first one is our GL load matrix, which basically you pass GL load matrix an array of 16 floats or doubles, and it sets the current matrix to whatever you pass it.
So you just basically populated the entire matrix with whatever you wanted to populate.
Exactly.
It with.
Remember when we're dealing with GL translate, scale, or rotate, it's modifying the model view matrix, but it's not actually us manually specifying exactly what the matrix is.
That's right.
Right. So with the load matrix, we can manually set everything up.
We get to set the cells.
Exactly. If we wanted to create our own custom transformations, let's say we wanted to do a mirror of some kind.
Now think about this, guys. So Joel, what Joel's talking about right now is we've got our model view, and it knows where our object is.
Right.
Perhaps he wants to do a mirror of that.
Right.
Okay, so he can set up a custom matrix, custom 4x4, that's going to have
a mirror operation.
In it. And then he can do a GL mult matrix.
Right, and that will stack or add on a mirror to whatever transformations are already there. So let's say, for example, that we... okay, let me think for just 1 second. Let's say we move our model over to 500, as we did in the example.
Right.
And then I want to do a mirror operation on that. So what we wanted to do is mirror it over to, say, -500. So we could write a matrix that would perform that transformation, multiply it onto the current transformation, and it would just copy right over, and it would do exactly what we want.
It's not really copy right over.
Right, I mean,
we're directly modifying the model view with the result of what we've just multiplied by. That's what's going on. And then, now we get into some super cool stuff.
That's right.
The GL push matrix and GL pop matrix.
These are two very, very important functions.
So important, Joel, that if you don't mind, I wouldn't mind if you jump back over to the whiteboard.
Will do.
And let's go and do a new layer real quick and just flood it with white.
Okay. Or can we just erase all that?
Or we can just erase it.
Or we can do that.
We sure can, if that makes you happy.
It makes me happy.
All right, so let's simulate drawing out
a biped.
A biped, yeah, there you go.
Okay. Watch my elite drawing skills.
How about we just start with one of the back spines, and then we go out to the
This is.
Oh, I can't laugh. Sorry.
No, you can't laugh. Hey, man, you're not much better, so you can't say anything.
It's because I'm at an angle.
Yeah, I know. So let's pretend this is a human being with a neck.
Is that his shoulders or elbows?
This is his elbows. Is that okay?
Oh, so he doesn't have two shoulders?
Oh, okay, we can put in shoulders. There, we have shoulders.
Okay. Now, in creating each of these objects, of course, it's very important to set up our model view matrix properly so that the object's drawn in the right place.
That's right.
And so, this is where you can see where pushing and popping is very important.
Yeah, and a quick description of what push and pop will do. Basically, it allows us to save the current state of our matrix and later restore it to what it originally was.
So before we make any modifications to it, we can say, we know that we're going to need to get back to this for whatever reason.
Right.
Push it. All right, now let's do some modifications, manipulate it, we draw something else. Now, perhaps we do that several times, and then we can start popping our way back out. Go ahead and walk through it, because this is a great example.
So let's say we're on the clavicle here.
Okay.
Or the neck, or whatever you want it to be.
The neck will work.
And then we draw this object. Okay. Then we need all of this arm here and this arm here are basically children of this clavicle here.
Let's label these. Like, we'll start there and say that one's A.
Okay. This one is A.
And then going off to the left, we'll say that is...
B?
Let's just do B, C, and D. This will make it easier to see on the stack.
Right. And
the other one, let's just do E, F, and G, because they just all represent...
This one, E, F, G?
Yeah, because they're just representing different...
matrices.
Yeah, exactly.
F and G.
Okay, so we start off at A. So this is the current state of our matrix, and we create our object in the right location.
Right, so we have our A.
Now, obviously, we're going to need to get back to this at some point in time.
Right. Once we want to draw B, then C, then D, and then we want to restore our state back to A.
So let's go ahead and pretend, let's draw a stack up there. Let's start putting these things on.
So let's start out with our A.
And so A is going to get pushed on first.
Right, so we got our A.
Okay. So now we reset our model view matrix.
Well, we don't reset it. We add on to it.
We modify.
We modify our model view matrix.
That's what I want to say. I don't even want to say we add on. We modify it.
Right.
In whatever way with whatever algorithm we need that is going to establish the new location of where B is going to be.
That's right.
So the model view has now been updated. It's been changed, and it's now the location of B.
Right.
So we create the object at B after we have set it or modified it.
So we're at B.
So let's go ahead and store where B is at. Okay, so now at this point, again, we modify the model view matrix in whatever means necessary to get us to the location of C.
Right.
And then once we do that, we can push C. And then again, we modify it to get all the way down to where D is, and we make the thing. Do we really need to push D?
We don't have to, but if there was anything else
if there was, yeah, absolutely.
So typically you would go ahead and push it onto it.
Okay. So now we need to get all the way back up to A so that we can then do the same thing on the other side.
Right.
So this is where we can start popping off our different model view matrices that have been stored on the stack.
Right. So at this point, we're at D, and we say, okay, pop this guy off. Okay. And so we're now at C. So we're currently at this location here.
Right. So each time you do a pop, you're then setting your model view matrix back to what it was before. Right. Okay. So what's popped off.
So if, let's say, he had an extra join here at this point, let's just say we needed to draw both of these.
Right.
Just as an example. I could go ahead and go back into whatever this guy was and draw him, so he could go back, just as an example.
Absolutely.
And then at this point, I go back to B, so I pop him off, and then pop B off, and now we're back to what A originally was.
Right, which now at this point we can then start working our way down E, F, G. You guys see how it works.
So we go to E, and then we go to F, and then we go to G, and then we work our way back up.
If you really think about what you're looking at, it's a parent-child, it's a hierarchical relationship.
That's exactly
that we're establishing, which is really, very cool.
Basically what you have, so in every single function that you create that draws a particular object, and basically all you would need to do is do a GL push and GL pop for every single object you do, and it would restore it to its original state.
Right. So the nice thing is if you were keeping track of where various objects were, after modifying the model view, after creating a particular object at a certain location, and then you always draw those guys accordingly. If you go back and update the one guy, the parent of all of those, even though when you pop these guys back off, they're going to have the objects drawn in the right location accordingly if the parent was modified. That's probably hard to understand with me just giving the verbiage. At that moment I was just demonstrating to Joel with my hands.
Right.
Because it works.
Right.
It really does work.
And I could draw a quick example here. Let's say I have a sphere.
Oh, let me do it.
Okay.
All right. I'm drawing sideways. So we have a sphere, and then we create, and of course we had to set our model view. And this is where we just created our object at, right? So now, of course, we set our model view again, and we create something over here. And let's just stick with 2.
Okay,
right?
2's good.
So let's say at this point, now, of course, we're keeping track of these things, that with this guy, then, we do something so that he's rotated or something, right? Since it's always relative.
Right.
That's the key right there. When this guy is put back into play, if you will. When we set the model view back to this, then he is going to also have done the exact same thing because it's a relative thing. It's the exact same thing you guys saw earlier when Joel was doing this and we made the sphere and then we made the square and then we made the cylinder up ahead.
Right.
If this GL translate was actually a little bit further over, wouldn't this guy have been a little bit further over too?
Yep.
So now isn't it like we're moving the parent around? And the child is moving around with it.
Exactly. So, yeah, perfect.
It's just cool stuff.
Yeah, very cool.
But the interesting thing is, those that are new to the world of OpenGL can so easily miss this.
Right, definitely. Because if you don't realize how this is working with the pushing and the popping, you can get really confused really quickly because you do a GL translate and everything after that is still affected by it, and you're going, why? You know?
It's like forward kinematics.
Exactly.
Dun, dun, dun.
and everyone that doesn't know what that means suddenly is lost.
Whoops, just pretend we didn't say that. So, anyways, now let us go ahead and focus at the low-level stuff now.
That's right.
So let's jump in there. Now that we've seen that we have the model view matrix, and we've talked about, let's go and jump back over to PowerPoint. And we've talked about several of the functions that we have to directly manipulate it, and store it and pull it back. Now let's dive down deeper into the model view matrix itself.
Right.
Okay.
So let's go to the next slide.
And before doing that, we have to talk about the identity matrix.
Well, these are some of the things that allow us to modify it.
Precisely.
So we kept saying resetting the matrix, and all we were saying is the identity matrix. So you'll remember from the intro, we called a GL matrix mode with GL model view.
And then we did GL load identity.
Right. And what this is doing is simply setting up a matrix with ones all along the diagonal. And we have this is our transformation matrix, which is a 4x4 for our model view matrix. And when there's ones all across the diagonal, this is the default state. Whatever vertex we multiply by this aren't going to get changed.
Right.
That's essentially what we're saying here. Because inside the pipeline of OpenGL, every GL vertex that you call is pushed out to OpenGL, and it multiplies that vertex by whatever model view matrix it currently has.
Right.
So when you multiply any vertex, any at all, to this matrix, nothing's going to happen to it. It's going to be in its original state.
So it's like if we say matrix A multiplied by an identity matrix, the answer would be matrix A.
Right. And as we kind of touched on in the last lesson, we said that if you take, let's say, matrix A times I, which is the identity matrix, it's going to equal I times that matrix because it's the same thing. It doesn't modify it.
Right.
So once that's out of the way, and that's with our GL load identity function. Now, for the interesting transformations.
So that you can find out what's going on
behind the scenes.
Yeah, in the actual matrix itself.
Right. So inside of here, remember we called the GL translate with 500 a second ago. And the matrix it would create is, you'll notice the identity matrix on the diagonal.
Right.
But on the last column, we would have 500. So whatever is passed in here is replaced in the last column here.
And exactly what he just said. A minute ago, when we created the sphere, the matrix at the very beginning, the very first time after initializing OpenGL, was the identity matrix.
Yep, that's right.
And so when we created the sphere, the X, Y, and Z, back up a scale if you don't, there we go. Slide, that's the word I'm looking for. So if you take your mouse and just kind of circle around the T, X, Y, and Z.
Right,
these guys are at 0.
Right.
So where was the sphere created?
At the origin. Exactly.
And then we said GL translate 500, so the upper right-hand cell changed over to a 5, and then the other two were at 00. Nothing else was modified within the matrix.
That's right.
And what happened? Our square was then created 5 units over.
Right.
So you guys can now see, in a very simplistic way, how we are modifying the matrix and how it is directly affecting things being drawn in our virtual world.
That's right. So if we jump back over to here, that's our GL translate. We also have our GL scale and rotate, as we said. Our scale modifies the diagonal in such a way that the first 1 cell, if you will, is the scale in X, the 2 is scale in Y, and 3 is scale in Z.
Right.
So we can either do uniform scaling, or we can do non-uniform scaling, in which, say, maybe the Y scales twice as much in X or Z or whatever. And
you can see why the importance of it being 1, 1, 1 with the identity matrix.
Right. If we set S, X, S, Y, and S, Z all to 1, then that's our identity matrix.
That's right.
And a GL scale with parameters of 1, 1, and 1 would do nothing.
Nothing.
Right.
That's right.
So that's our scale. Very, very simple. But then we get into the GL rotate. And this
right now, several of our viewers just
fainted.
Exactly.
So the three basic operations that we can have with a rotate is the rotate around the x-axis, y-axis, and z-axis. The GL rotate function that we have in OpenGL allows us to rotate around any axis. The last 3 parameters you see in the GL rotate call allows us to specify which axis we rotate around.
Now, theta is going to be in a clockwise direction, correct?
Right.
Okay.
And theta, as I mentioned, I think in the vector class, this is all in degrees.
Right.
When we're working with cosines and sines, if you worked with math.h, the functions inside of there, everything is always in radians.
Right.
But when we move over into the world of OpenGL, for some unknown reason, they decided to use degrees for everything, just to mess with people. So always remember, when you call GL rotate, everything is in degrees. So let's look at our first rotation matrix here. You'll see that we have rotation around x, and we have our cosine theta, sine theta, negative sine theta, cosine theta. And remember, as we mentioned in the matrix class, the first column here is the x-axis, then we have our y-axis, and then we have our z-axis. When we're rotating around the x-axis, remember, we're not modifying anything that's on that axis. We're only modifying that which is on the YZ plane.
That's right.
So only those that are on these two axes are actually getting modified.
Which makes sense.
Which does make sense. The X in the last column are equal to the identity matrix version.
And you kind of have to look a little bit in the future, but you already know this. Remember, what are we doing? We're doing multiplication. We're multiplying against the model view matrix. And so we have a value of 1, and then zeros all the way across.
Right.
And we multiply that 1 by whatever's currently there. You can see how we're not changing it.
Exactly. And so these are getting modified.
That's right.
And then this one isn't. And the same goes for the y-axis. Y-axis isn't changed.
And same thing for Z.
Same thing for Z.
Makes sense.
And another thing just to point out, we show the rotate around X, Y, and Z. Of course, there are other formulas that allow you to rotate around an arbitrary axis that you can create manually. Those are a lot more complex. And there is actually a theorem that says that if you rotate around just rotating around X, Y, and Z axes, you can get any rotation you want.
Oh, Euler.
Yes, Euler theorem. So with that, I think
and a lot of you guys have seen that, like in 3ds Max, for those of you that are Max users, and you can select what type of controller for like rotations.
Right, exactly the same thing.
Cool stuff.
So with that, let's see a little bit of an example.
Yeah. Now, first of all, Joel, why is it important to even show low level of stuff? I mean, come on, we have GL, translate, rotate, and scale. We don't have to know this complex math stuff, do we?
And for the most part, you're right.
Unless we want to do anything fancy.
Unless you want to actually utilize OpenGL to its fullest potential.
Well, you want to make a mirror operation like you just said a minute ago.
Exactly. If you want to truly grasp the power of OpenGL, you need to understand how all of this stuff works.
That's right.
Because your GL mult matrix, your GL load matrix would be totally useless. If
you would never use them.
You would never use them.
That's right.
And a lot of people don't ever use them, and you don't get complex programs. So in this simple example, all we're doing is moving the object to 2, 5, 7, rotating it negative 45 degrees counterclockwise around the z-axis, and then scaling that object. So internally, what it's doing is adding up all these transformations. Remember, we have one model view matrix, and it's storing up all of these transformations that we do. So all of these things are stacking up together.
Right.
So how do we condense everything, all these different transformations, into one matrix? You multiply them together.
That's right.
So in this case, you'll notice that we have our GL translate here, our GL rotate here, and our scale here. What's going on? Well, this is pre-multiplication. This is important because otherwise everything would be opposite. So in this case, we're multiplying the translation matrix, and we're putting that ahead. We're multiplying. We're taking. Okay, let me back up for a second. We take our translate matrix and multiply that by our model view matrix. And in this case, what we're doing is combining all of those into our final transformation matrix, which would be stored inside of our model view matrix.
Okay.
Does that make sense?
I think they still may be wondering, why are you starting with scale?
Okay. Everything is backwards, right?
Right.
So we have our model view matrix. Basically, okay, let me try to see a good way to explain this. Everything is pre-multiplied inside of OpenGL. Otherwise, if you didn't pre-multiply, you would scale first, then rotate, then translate.
Okay.
And so if you pre-multiply everything, everything will be in the order that you specify.
Okay.
Does that make sense?
That's better.
Okay. So let's go ahead and switch over onto our whiteboard and actually do this.
Okay.
This is going to be a lot of fun, I think.
All you guys got to remember is dot product.
That's right.
And
lots of
and not to get bored.
So the first thing is we're
going to multiply this is really an important thing to understand. As we just saw that we've got 3 different matrices that we're going to be multiplying. We're going to start by first multiplying the first 2. So we've got scale on the left, and then right above we've got our rotations.
Right.
So we're going to multiply that out first. Then we're going to take the result of that and multiply
by the
translations to have our final transformation matrix.
That's right.
Okay.
And the first thing is you'll notice we have this cosine of negative pi over 4, which a second ago was in 45 degrees, right?
Right.
And we're like, well, why did you just convert it over into radians? Well, we did this simply because, remember, inside, if we're going to create our own matrix, this is all in radians, right?
Right.
So if you're going to pass it to the cosine function inside of C's basic calls, you would need to convert it into radians first.
All right, let's go ahead and jump down into the bottom corner and talk about converting back and forth between radians and degrees.
All right, so let me
just in case anyone has forgotten. Whoa, that's scary.
Yes, let's create a new layer. All right, so remember, if we have our pi is equal to 180 degrees.
Right.
Right? Mm-hmm. So if we want to convert between these, it's not actually that difficult to do. All we would need to do is say, let's say we have some in degrees. Would you want to do a test example? Let's say our 45 degrees.
That sounds great.
All right. So we have our pi, and we're looking for some degree x in radians, right?
Right.
And this is going to equal 180 degrees over our 45 degrees, right?
Mm-hmm.
So this is a simple ratio that we've set up. So all we need to do is if we reduce this and pull this guy over to here and flip these two around, that probably sounded really confusing.
Awesome. Let me just work it out in my head and occasionally throw some words out.
So we would have 45 degrees times pi
right.
divided by 180 degrees. So if you reduce this, what you get is pi over 4. And which makes sense, too, because if you take 180 degrees, divide that by 2, you get 90 degrees, right? Mm-hmm. And if you divide that by 2, you get 45 degrees.
That's right.
And so, bingo, there you go.
It does.
So, a simple refresher on some radian stuff. Now, so if we convert this over, a lot of you probably remember your cosine of 45 degrees is root 2 over 2. And so on. So let me go ahead and convert this over into something, or 1 over root 2, however you want to say it.
Right.
So we have our matrix that's converted over.
Right.
Everything good?
Mm-hmm.
Okay. So let's go ahead and do this matrix multiplication.
You guys remember how this goes. Basically, it's just, it's the drawing of the line.
So, right. This line goes to here. This line goes to here.
And then it's just finding the dot product.
Right, so we have 2 times 1 over root 2.
Yeah, so basically what we're going to end up with, just simplifying it down, is going to be a square root of 2.
Right, so, I mean, let me just write this over here real quick. If 2 multiplied by root 2...
okay, you're going to show them how
so we have 2, 1 over root 2.
Which equals
2
over
root 2.
Yeah, times...
Which you could, if you want to simplify, you could
root
multiply
2
this...
over root 2...
Which is, this is 1, so we can multiply it by 1.
Right.
And then these two become 2, so you get 2 times root 2 over 2.
And you can cross out the 2 2's.
These two cross out, and you get root 2.
Okay, sorry, I didn't mean to jump the gun there.
That's all good.
So basically what we're going to get as we work our way across, the first one, if you take the dot product all the way across, is going to give you root 2.
Right. And then the second one, this line with this line.
Negative.
So you get negative
root 2.
Root 2.
Yeah, so same thing except negative. You can see it right there.
Right.
And then, of course, the last two are real easy. It's just zeros.
Yep.
Now, on the next line, we're going to have 1 over root 2.
So you can see here we have
0 and then
1.
Yep.
Just want to make sure they're getting it.
And
Thank
there
you.
you go.
Wow, it just appeared.
And then the next one's going to be 1 over root 2. Mm-hmm. And then, of course, you can see the other one's real easy. 0 and 0.
0 and 0.
All right, next line down. We start out with 0 and 0. Quite simple. Good old multiplication by 0. And then we're going to have 3.
Right. If
you can show
this one goes all the way to here, and this one stops here. So 0 times 0 plus 0 times 0.
0.
Plus 3 times 1
is 3. Plus 0 times 0 is 0. The answer is 3.
Right.
There, you got one worked out all the way. And then finally on the last one, that's 0, 0, 0. And you can see, 1.
Yeah, it's pretty obvious.
That's real easy to see.
All
right, so that's step 1. This is a 2-step process. Mm-hmm. We now need to take this result, because this is the result of multiplying the scale by the rotate.
Right.
Now we need to take this result and multiply it by the translate to have our final transformation.
Right.
So
let me go ahead and erase this out just really quickly. And now let me bring in my translate layer. So this is our translate matrix.
So now when we go to draw our line, we're drawing from our result now all the way over. Yeah, and this is where we're coming up with our new answer. Woohoo!
Lots and lots of multiplying.
But it really is simple stuff, guys.
Right.
The problem is it's just, you're going to multiply 2, I'm looking at like square root of 2 times 1 plus the square root of 2 times 0 plus the square root of 0 times 0 plus the square root, 0 times 2.
The square root of 0.
You just get to talking so fast. That's what I mean. It's boring.
Yep, it is.
It's tedious. And it's very easy to lose count and track.
And make a mistake.
Yeah, when you've got a very large matrix and it's just boring numbers. So basically, as we work our way across, what we end up with is going to be the square root of 2. And then we end up with a negative root of 2, 0. And then we end up with 3 times Negative 3 times the root of 2.
Right.
All right.
Don't worry, I worked it on my head.
Next line is going to be 1 over the root of 2. And again, 1 over the root of 2. And then the next one's real easy to see. It's just 0. Then we end up with 7 over the root of 2. And now it's going to get a lot easier for you.
All right.
0, 0. Now these two special just for them.
Let's work them out. You'll notice that this goes
0,
this goes across all the way to here, and this one comes down. So 0 times 0 plus 0 times 0 plus 3 times 1 plus 0 times 0 is 3.
And let's do the next one.
All right, this line goes to here, this line goes to here. So 0 times 2, 0 times 5,
0.
3 times 7 is 21, and then 0 times 1 is 0.
So the answer is going to be 21. So there, haha, you guys got to see 2.
That's right. So then this last row is going to be 0, 0, 1.
And that, my friends, is our
final transformation matrix. Exactly. And exactly, we did it. We pre-multiplied. So in this case, this one matrix right here does all 3 operations for us. And that's what our final model view matrix inside of OpenGL would actually look like.
Right. So if we were now to affect this.
And just one quick thing.
Okay, yeah.
What this is doing here, it's going to translate it first. This one model view matrix is going to translate our object, rotate our object, and then scale our object. Mm-hmm. And again, it's pre-multiplied, so everything works smoothly in the order that we want it to work in.
Correct.
So,
but what does all this mean?
Yeah, what does this mean? We have our transformation matrix. That's all fine and dandy. Let's say we have some vertices for, say, our cube or something like that.
Let's pick on a single vertex right now. What's going to happen to it? Let's say that we have a vertex that's located at 4, 2, 1.
All right, so we want one that's at 4, 2, 1.
Right.
Inside of OpenGL, everything is in 4 dimensions.
That's right.
So it has an extra dimension for good measure, and we'll talk about that a little bit more later. So if we want to convert this over to one extra one, because remember, this is a 4x4, just to drive this home. Don't want to beat a horse to death, but this is important. So if we have
a little arrow going up to that guy.
Okay, this one is this guy right here.
4x4 matrix, right.
So if we used this would be a 3x1, right?
3x1, and that the crossway 4 and 3 is not compatible.
Work. Right. So what you need to do is convert this into a 4x1.
That's right. So let's go ahead and draw that vertically. Mm-hmm. So put a little time symbol down there.
Okay.
Because we're going to multiply, and then, let's do it vertical. So you're going to have 4, 2, 1, and we're going to throw a 1 in there.
Right.
So that we're now compatible.
This is known as the W coordinate inside of OpenGL. So you have your X, Y, Z, and then a W guy.
Right. So this equals.
So this will actually give us a 4x1 matrix, or a vector in this case.
How cool is that?
Yeah, very cool. So let me go ahead and just kind of move this over a little bit. Let me hide this real quick so I have some extra room to work with. Hide, thank you. Equals. And then you simply multiply this out. So if you move this up, you would have square root of 2 times 4 plus negative square root of 2 times 2 plus 0 plus negative square root of 3. Negative 3 square root of 2.
Right, so you're going to end up with a negative root of 2.
Negative root of 2.
And then if you continue working your way down, we're going to have 13 over the root of 2. We're going to have 24. And we're going to have 1. And you guys are more than welcome to work it out all the way.
That's right. This is just to show you exactly what's going on behind the scenes. So this is happening for every single vertex that you create.
So what does this represent? What's this new guy represent?
This represents our vertex that has been transformed, translated 257, rotated negative 45 degrees, and scaled.
So it's our new position for it?
It's our new position for our vertex. So this one vertex here at 421 was transformed.
After it was scaled, rotated, and moved, this is where we're at.
This is where we're finally at.
How cool is that?
Very cool.
All right, so this is pretty much it, Joel.
Yes, it is.
This has been a big look at transformations.
And there's a lot here, so don't freak out about this. Yeah. But at the same time, this is very important to understand. I mean, if you don't understand how this works, you will get stuck eventually.
Yeah, for sure. Well, if you want to do anything cool, you're going to get stuck. More importantly, if you don't understand how this works, to be dead honest with you, I mean, because of the use of dot product and some of the simple mathematics in here, you're going to get stuck even sooner.
That's right.
So keep that in mind. I mean, it may not be the creation of some sort of cool modification that you're going to do to the model view matrix that's going to get you stuck, but just the basic mathematics itself is going to get you locked up elsewhere.
That's for sure.
But I'm really happy with this video because I think this does a fantastic job of tying all of our math ones together and taking us all the way back to the introduction video and making the whole model view matrix a little bit more clear.
Right.
The GL load identity a little more clear. And you guys at this point are now starting to see exactly what's happening inside OpenGL in reference to it being a state machine.
Right.
Not only that, but they also got kind of a look at hierarchies too.
Yep, which is very cool.
So with that is going to wrap up this video on transformations. Thanks a lot, everyone.